COVID-19 pandemic, terms like R0, herd immunity, and epidemic curves became household words, but these concepts have been fundamental to veterinary epidemiology for decades in designing vaccination programs for livestock, evaluating outbreak control strategies, and understanding why some diseases are easier to eliminate than others. In this talk, we'll demystify the mathematics behind these concepts. We'll build compartmental models, the SIR and SEIR frameworks from the ground up, derive the basic reproduction number R0, and explain what it predicts, calculate the herd immunity threshold, and what it means for vaccination coverage, and distinguish vaccine efficacy from vaccine effectiveness. These are some of the most powerful conceptual tools in all of population health, and by the end of this talk, you'll understand exactly why they matter. Compartmental models are the mathematical framework we use to describe how infectious diseases spread through populations over time. The idea is elegant. Divide the population into compartments based on disease status and model how animals flow between compartments as the epidemic unfolds. The simplest model is SIR. Every animal in the population is in one of three compartments: susceptible, not yet infected and at risk; infectious, currently infected and capable of transmitting; or recovered, no longer infectious and immune. Animals move from S to I when they encounter and are infected by an infectious animal at a rate determined by beta, the transmission rate. They move from I to R when they recover at a rate determined by gamma, the recovery rate. The SEIR model adds a fourth compartment, exposed or latent, between susceptible and infectious. This compartment represents animals that have been infected but are not yet infectious, the incubation period we discussed in Talk 6.2. Animals move from E to I at a rate determined by sigma, the incubation rate, which is the reciprocal of the average incubation period. For diseases with meaningful incubation periods, which is most of them, SEIR is more realistic than SIR. These models make predictions about epidemic trajectories. How fast will the epidemic grow? When will it peak? What proportion of the population will ultimately be infected? And critically, what level of immunity is needed to prevent epidemic spread? That last question is answered by R0. Not is the basic reproduction number, and it is arguably the most important single number in infectious disease epidemiology. It tells you the average number of new cases one infectious animal would generate during its entire infectious period in a population where every animal is susceptible. The threshold logic is straightforward and powerful. If R0 is less than 1, the average case generates less than one new case. The chain of transmission is broken more often than it continues, and the epidemic fades out on its own. If R0 equals 1, every case replaces itself exactly. The disease persists at a stable endemic level. If R0 is greater than 1, every case generates more than one new case. The number of infected animals grows over time, and you have a growing epidemic. The formula R0 equals beta divided by gamma, transmission rate divided by recovery rate, tells you that R0 is high when animals transmit efficiently and remain infectious for a long time, and low when they recover quickly or transmit poorly. You can also think of it as the product of three components: how many contacts an infectious animal has per unit time, the probability that each contact results in transmission, and the duration of the infectious period. The veterinary examples on this slide are instructive. FMD in a naïve cattle herd has an R0 of 8 to 15, meaning every infected cow generates 8 to 15 new infections in a susceptible herd. That's why FMD outbreaks spread explosively and why rapid aggressive control measures are mandatory. PRRS in a naïve swine herd has R0 of 3 to 5, still well above 1, still capable of rapid spread, but somewhat more controllable. Seasonal influenza, by contrast, has an R0 of around 1.2 to 2, above 1, which is why it sustains itself each season, but low enough that moderate vaccination coverage can substantially reduce transmission. R0 describes transmission dynamics in a completely susceptible population, but real populations are rarely completely susceptible. Some animals have recovered from infection and are immune, some are vaccinated. As immunity builds, the effective reproduction number RE falls. RE equals R0 multiplied by the proportion of the population still susceptible. As the susceptible fraction decreases, RE decreases. The critical threshold is RE equals 1. When RE falls below 1, when the average case generates fewer than one new case, the epidemic cannot sustain itself. Even when new cases are introduced, each case infects fewer than one additional animal, and the chain of transmission fades. This is herd immunity. The herd immunity threshold, HIT, is the proportion of the population that must be immune to drive RE below 1. The formula is 1 minus 1 divided by R0. For a disease with R0 of 2, 50% immunity is sufficient. For R0 of 4, you need 75%. For an R0 of 8, you need 87.5%. For FMD with an R0 around 10 to 15, you need 90% or more of the herd immune to prevent epidemic spread. This is why FMD control in naive populations relies on rapid, aggressive vaccination of the entire herd, not just sick animals, simultaneously with movement restrictions and culling of clinical cases. You need to push RE below 1 as fast as possible, which requires getting most of the population above the immunity threshold in a very short time window. It's also why even a small gap in vaccination coverage can allow a pathogen with high R0 to reestablish. A herd with 85% vaccine coverage sounds well vaccinated, but for FMD with an R0 of 10, an 85% immunity level leaves RE at 1.5, above the epidemic threshold. The herd is not protected despite relatively high coverage. Efficacy and vaccine effectiveness are related but distinct measures that we first introduced in the efficacy effectiveness framework in Talk 5.2. Let's now connect them to population level immunity and herd immunity thresholds. Vaccine efficacy is measured under ideal controlled conditions, usually a randomized controlled trial with carefully selected animals, standardized vaccine handling, and controlled challenge or natural exposure in a research setting. The formula is 1 minus the relative risk of disease in vaccinated versus unvaccinated animals times 100%. If vaccinated pigs have an 8% risk of PRRS and unvaccinated pigs have a 20% risk, VE equals 1 minus 0.4 times 100%, which equals 60%. This means vaccination reduced the risk of disease by 60% under trial conditions. Vaccine effectiveness is the performance of the same vaccine in the real world, measured through observational studies in field conditions. The same formula applies, but now the ideal conditions assumption is gone. Cold chain failures degrade potency. Farmers may not vaccinate all animals. Timing may be off relative to pathogen exposure. Concurrent infections may blunt the immune response. The result is almost universally lower than efficacy, sometimes dramatically lower. The effectiveness gap between efficacy and effectiveness is one of the most important practical concepts in vaccination program design. A vaccine with 90% efficacy in a trial might have 60% effectiveness in the field. And if your disease has an R0 of 4 and you need 75% immunity for herd protection, that 60% effectiveness may be insufficient even with 100% coverage. This is why vaccination programs must address cold chain integrity, coverage verification, timing protocols, and concurrent health management, not just procure a vaccine with good trial efficacy. Vaccine coverage. The proportion of the target population actually vaccinated is distinct from efficacy and effectiveness. Even a perfect vaccine with 100% efficacy provides no population level protection if only 50% of animals receive it. Coverage must exceed HIT divided by efficacy to achieve true herd protection. Required coverage equals HIT divided by VE. SIR model makes predictions about epidemic trajectories that are counterintuitive but important. Let's walk through them. At the start of an epidemic in a naive population, the number of infectious animals is small but growing exponentially. Every case generates R0 new cases, and those cases generate R0 more. The epidemic grows rapidly while the susceptible pool is large and RE is close to R0. As the epidemic progresses, the susceptible pool depletes. Some animals are infected and move to I, and recovered animals move to R. As S shrinks, RE, which equals R0 times S divided by N, falls. The epidemic peak occurs exactly when RE passes through 1. The number of new cases exactly equals the number of recoveries. After the peak, RE is below 1. New cases are generated more slowly than recoveries occur, and the epidemic declines. Here's the counterintuitive insight. The epidemic ends before all susceptible animals are infected. Even at the peak, there are still many susceptibles in the population. The epidemic stops because RE has fallen below 1, not because there are no more susceptibles. This is the epidemic's natural breaking mechanism. The depletion of the susceptible pool drives RE below 1 and self-limits spread. Interventions accelerate this breaking. Vaccination moves animals from S to R without going through I. It shrinks the susceptible pool much faster than natural infection would, driving RE below 1 before as many animals are infected. Isolation of infectious animals effectively reduces beta, the contact rate between I and S animals. Culling removes infectious animals from the I compartment entirely. All three interventions lower RE through different mechanisms, and all can be used simultaneously for maximum effect. Summary. SIR and SEIR models partition populations into disease compartments and model flow between them. R0 is the fundamental epidemic parameter. Below 1 means extinction, above 1 means growth. The herd immunity threshold is 1 minus 1 over R0. Higher R0 diseases require higher coverage. As immunity builds, RE falls. Epidemics stop when RE crosses below 1. Vaccine efficacy and effectiveness are different measures. The effectiveness gap between them is real and must be accounted for in program design. Required vaccination coverage equals HIT divided by vaccine efficacy, and all effective interventions work by lowering RE through different routes in the model. In the next talk, our final in Unit 6, we connect all of this to endemic and epidemic disease patterns, the spectrum from disease control to eradication, and the individual and population level determinants of health. Pause the video and read the scenario and try to work through the questions on your own. Then we'll work through them together. This scenario is designed around a realistic and important veterinary problem. Ovipneumoniae is a pathogen of genuine concern in both domestic sheep and, critically, in bighorn sheep, where contact with domestic sheep has caused devastating pneumonia epizootics. The R0 of 4 is realistic for this pathogen in naive populations. Question 1. Herd immunity threshold. HIT equals 1 minus 1 over R naught equals 1 minus 1/4 equals 1 minus 0.25 equals 0.75 equals 75%. 75% of the 200 ewe flock or 150 animals must be immune to prevent epidemic spread of Mycoplasma ovipneumoniae in this population. Question 2. RE after introduction. First, calculate the number of susceptibles immediately after the introduction. Establish ewes, 180 total, 150 immune, so 30 are susceptible. 180 minus 150 equals 30. New ewes, 20, all naive, so 20 susceptible. Total susceptibles equals 30 plus 20 equals 50. Susceptible animals out of 200 total. Susceptible fraction S divided by N equals 50 divided by 200 equals 0.25. RE equals R naught times susceptibles over N equals 4 times 0.25 equals 1. With RE exactly equal to 1, the population is at the epidemic threshold. The disease can persist at endemic equilibrium, but is not expected to produce an expanding epidemic. The introduction of 20 naive ewes has pushed the flock from below the epidemic threshold to exactly at it. In practice, with stochastic variation and the 6 subclinical carrier animals actively shedding, the realized RE may push slightly above 1, meaning a modest outbreak is plausible. Question 3. Required vaccination coverage. Required coverage equals HIT divided by VE equals 0.75 divided by 0.8 equals 0.9375 equals 93.75%. Nearly 94% of the 200 ewe flock, or approximately 188 animals, must be vaccinated to achieve herd immunity given an 80% efficacy vaccine. Question 4. Is herd immunity achieved with 80% coverage? Of the 50 susceptibles, 80% coverage means 40 susceptibles vaccinated, of whom 80% times 40 equals 32 gain immunity. The remaining 8 susceptibles vaccinated don't develop immunity, plus 10 unvaccinated susceptibles remain. Total immune in the population, 150 are naturally immune, plus 32 newly vaccinated susceptibles who responded, equals 182 immune out of 200. The proportion immune equals 182 divided by 200 equals 91%. This exceeds the HIT of 75%. Herd immunity is achieved with this vaccination program. The producer should still be counseled to 1. Identify and potentially remove the 6 subclinical carrier ewes as a long-term reservoir management strategy. 2. Apply a quarantine protocol to all future introductions with pre-testing for Mycoplasma ovipneumoniae. And 3. Maintain vaccination coverage above 94% at each subsequent cycle to sustain herd immunity as cohorts turn over.